Well, I'm honored to be the first speaker of the first lecture series of TechnoTalks. I was informed about it, told it had to be computer related, and I thought to myself, I'm not really a computer expert. I'm an engineer, but the truth is these days engineers use computer tools a lot. It doesn't mean they don't use their heads, but it means they've got a lot of tools that they never used to have, and they're virtual tools. Okay? So where an engineer used to show up at work looking like Mickey on the left, now he shows up and sits in a chair. Not entirely, but the truth is, the engineer today has to be able to do both. Because sitting at a computer alone doesn't produce anything. But it does make the design process go a lot faster. And what you can get at the end is a much more optimized and well, much better design actually using these tools. So the Engineer's Virtual Toolbox is the name of this presentation. I hope at the end of it you have a better idea of what an engineer does and what tools are at his or her disposal. All talks that I do stem from this website I have called the Engineer's Pulse. There's three main focuses on this website. Science education, where you see a free body diagram on an airplane. There's philosophical discussions, time, God, all kinds of things. And also, I talk a lot about evolving technologies. Here you see a picture of the space elevator, which happens to be a project I've worked on for many years. It was the subject of my master's thesis. And I actually go to the conference most years. There's a North American Space Elevator Conference that takes place in Seattle. And I've had the pleasure of speaking there before. But yeah, if you find science interesting and you like to learn more about how it affects our lives, the Engineer's Pulse on blogspot.com. I have posts up there once or twice a week. They're all articles pertaining to, it's trying to relate science to life, and not only for science students. It's really trying to make science accessible. Not really physics and engineering, but really anything. So for this presentation, I'm going to talk a little bit about what an engineer is, talk about two approaches to handling any problem, be it pen and paper or a virtual tool, and talk a little bit about a job I had before I began teaching in engineering. So an engineer is a lot of things. First and foremost, I guess it's a problem solver. Usually the problem is based in science. The main thing an engineer has to do is look at what is being asked. What's the problem? And provide a solution. And usually between the problem and solution, there's design and analysis. There's some sort of design and analysis going on. And there's really three things that's usually asked of an engineer. Make it good, that means it has to work. Make it cheap, it means it should be inexpensive. And make it fast, it means they want it tomorrow. So these are three things, but in reality you can't do all three. And that's where optimization comes in. For example, the saying goes you can only have two. These are you want it good, cheap, and fast, you have to pick two. The others you're going to have to bend. So if you want it fast and you want it cheap, it's not going to work. But if you want it good and your priority is to get it quickly, it's going to cost something. Because you may have to use off-the-shelf parts that are expensive. And what would be the other one? That's where you want it cheap. Well, it could take a long time to design something using completely new parts. And so in the end, you want something that's going to be mass efficient. So anyway. So what does an engineer do? I'll tell you what they don't do. They don't spend their entire day doing what you do in school. You don't spend your entire day drawing free body diagrams. But we do use the things we learned in school, at least when conceptualizing a problem. This thing you see here is part of an NYC physics course. It's a spring damper system. But while very simplistic, we learn the basics here, and in future we learn, in practice we learn that this is actually could be the suspension system of a wheel on a car, and you have four of them, and you can actually animate how a car might work, might bounce in response to a bumpy road. And you design these guys based on the differential equations that apply that we learn in an engineering program. So there are two ways to approach. Is the pen and paper way, which is what we learn in school, and then there are virtual tools, which these days engineers spend much more time doing. So the pen and paper approach, it's kind of like school. It's the analytical method. The difference is, in school, there's no friction usually, or if there is, it's simple enough. A lot of approximations. And in practice, we do use this idea, but we take our complex problem, which we can't solve with pen and paper alone, precisely, convert it to a simpler problem we can solve very well. And then we get a solution that's not perfect, but it gives us a first cut. It gives us an idea of where we're headed with our design. And that's when we begin to step into virtual tools. This is where we iterate through our design process. So the other method would be called analytical, whereas numerical tools are what's done on computers. Numerical method. This FEM analysis is huge in engineering. It's just about every engineer uses it at some point. It's called the finite element method. That's what FEM stands for. And you have a pre and post processor like FEMAP, and the actual math equations are being solved numerically using something like Nastran. A few different softwares, but these are a couple of popular ones. So I'm going to talk a little bit about how these work. You know, it's not, you can look at a car from a distance and say it's a big mass, and let's look at the forces acting on it. That's nice, but when you want to know what's going on within it, the internal stresses, you need to use virtual tools to get a precise result. Or get approximate result, and if you didn't have the tools, like we didn't used to have the tools, you would add mass, make it stronger than it needs to be. It would be heavier, but you'd get, you know, you'd account for the fact that you're not going to be as precise by over-designing. Well, now we have these tools and we want to save on mass and cost, so we use them. So what's actually being done? Whether your model's a motorcycle, a car, or a satellite, doesn't matter what it is, you can break it up into tiny little components. So whereas you might look at the whole thing as a structure when doing pen and paper, what the computer does is you put in the properties, you put in this huge structure that's very detailed, very precise, and you break it up, it breaks it up, you break it up with it, into tiny components, a lot of little components for which the computer can actually solve the science going on, the physics going on for a tiny component. You can break it up into thousands or even millions of little elements there. So rather than only looking at the structure, the computer says, well, I know how this element works, and I know what elements it's attached to. So once you've imported this, you make your structure, so it has all its components, and you want to see how it's going to react in a certain environment. That means it's crashing, or there's air resistance, whatever the environment is, and then you run Nastran, which solves all those equations. It does the physics for you. And then you can examine the results, and that's what you see here. These are color plots of, this one looks like heat transfer, the thermal plot on a motorcycle, and this one here would be the stress in the different components of a car as it's crashing. Okay, so that's the approach there. And then you look and you can see where your maximum stresses are, and you can see where you need to reinforce the design and so on. And there's an iterative process where you click and it solves again. Maybe you strengthen a few trouble spots and you check. So there are two reasons to use that previous approach. One is to save time. Although it takes quite a bit of time to design in those initial designs, anytime you make a change, you can very quickly press click. And what the software does is solves thousands of equations. You would sit there the rest of your life solving one problem. It does it in seconds. And this is where processing has saved the engineering industry a lot of time. A satellite used to take 2 years to design. Now you get something in 6 months. And what's amazing, so we saved up to 4 times, the design phase was 4 times shorter. What's amazing is the result. That thing that you designed in only 6 months is now lighter and cheaper. And the reason is we didn't have to make it so heavy. We were very precise in our analysis. And the parts we can use are lighter. And as a result, why does that make it cheaper? Well, if you're talking about a satellite, every kilogram costs you $10,000 just to place, just in lifting costs. So in this industry, in the space industry in particular, every gram is accounted for. So this is a huge thing. But there is a catch. It's one thing to let the computer do the work for you, but this should really be avoided. And there's a danger when you have these amazing tools at your disposal that you'll distance yourself from the actual science going on. But I recommend people don't do that, or they'll look like this. Virtual tools are wonderful if the person using them realizes that they're just a tool. They shouldn't be trusted blindly. So the reason we need both approaches is the first one put us in the ballpark, and if the second one is off by a lot, we know something's gone wrong in our numerical analysis. They have to jive, and if they don't, we have to recheck, see if there's an error in our model that we've imported, or maybe our hand calculations were wrong. But they have to be in the same ballpark, same order of magnitude. And in the end, an engineer has to have common sense. Just because someone said this was a good idea, doesn't mean they should have printed a 625 mile per hour maximum limit for a sign. So in the same way, when an engineer says, well, the computer said so, that's not an acceptable excuse for a failed design. You have to ask yourself if the solution makes sense. Common sense can be overlooked when all you're looking at are a screen filled with numbers. You have to always know what you're talking about, and then you can say, do the result